Hi, hello. This is Prof. Nanius, and we're going to look at some aspects of partial derivatives. I consider this to be an optional video for my class, but what we're going to look at is an example of a function that is not continuous at the origin, but has both partial derivatives defined at the origin, but not continuous. So let's get to it. And there we go. And let's just get to our screen here. Now, let's, as in Calc 1, one of the things, and that ought to make the screen a little bit bigger. Uh, there it is. Should have had this done before. But anyway, in Calc 1, we learned that if f is differentiable at a, then x is continuous at x equal a. And basically the sketch of that is that if f is differentiable, then the limit as the change in x approaches 0 of f of a plus change in x minus f of a over change in x must equal some limit L, which is the derivative. And then we learn that delta x is equal 0 is strictly not in the domain, so we can multiply both sides by delta x. And let's rephrase that. We can multiply both sides by the limit as delta x goes to 0 of delta x. And we get this. A plus delta x minus f of a over delta x. And that must equal, and I did not plan ahead again. And there it is. Widen this a bit. It's going to be the limit as delta x goes to 0 of delta x times L. Now, because L is a finite number, this side is 0. And in calculus, you learn that the limit of the product is the product of the limits. So this goes inside. And we have this. And it's a limit of that. The delta x's, of course, cancel. And so we see that the limit as delta x goes to 0 of f of a plus delta x minus f of a is 0. And then doing a little bit of limit calculation, we see that the limit as delta x goes to 0 of a plus delta x must equal f of a, which means that f is continuous at a. And this is true. So I'll just make a parenthetical comment here. This is true even if the derivative function is not continuous at x equal a. And there are functions that have discontinuous derivatives. There's many of them. Probably one of them, well, I don't want to get too far afield into that. But the upshot in Calc 1, we learned having a derivative at a point meant the function was continuous at the point. However, in multivariable calculus, it is possible to have partial derivatives at some point a, b, but for the function to not be continuous. And I'll demonstrate such a function. So let's consider the following function. Consider f of xy equals xy over x squared plus y squared for xy not equal to 0, 0, and equal to 0 at 0, 0. Now, the very first thing, and we did this in class, but the first thing to note is that f is not continuous at the origin. And the reason for that is, let's approach 0, 0 along the line y equals mx. And I won't even bother to specify m. And let's take a look at what happens if we substitute mx for y. Let's take a look at what happens. The limit as x goes to 0 of f of x mx. Now, because that's not 0, we're getting to 0, we don't have this. So this will be the limit as x goes to 0 of x. We substitute mx for y. And remember, what we're doing is we're approaching the origin along the line y equals mx. And technically, you're approaching it from both sides. I haven't, here m is positive, but it could be negative as well. The bottom, you have an x squared plus mx squared. And then we do a little bit of algebra. We have m, we have x squared times m. On the bottom, we have x squared plus m squared x squared. Bottom, we have an x squared, 1 plus m squared. And notice what happens to the x squareds. This turns out to be m over 1 plus m squared. Now, I know some people don't like the term cancellation, but that's really what's going on. And this varies with m. In other words, if you let m be different numbers, you get different numbers here. Like m equals 0, you get a 0. M equal 1, you get 1/2. Those are not equal, and they're certainly not equal to 0. So we've shown that this function right here is not continuous at the origin. Okay? And let's see here. So, that's slide 1. Oh, well, this antiquated thing. Let's go back here. Let's go back to this thing. Oh, this is just a disaster here. Now let's. This is what happens when you don't update your computer. Now, let's go ahead and look at the partial derivative. Now, I'll do the calculation for one of these. So let's calculate the partial with respect to x at 0. So this is f sub x at 0, 0. Well, as you know, that's going to be the limit as xy goes to 0, 0 of f of Yeah, this is, oh, I screwed that up again, darn it. You didn't see that? Let's get rid of this nonsense here. I was back on continuity instead of partial derivatives. And get rid of that. Kind of bumbling today, but this is a limit as the change in x goes to 0 of f of 0 plus change in x, 0 minus f of 0, 0 over the change in x. Now, remember, in our definition here, at 0, 0, that's just a 0. So this is just going to be the limit as delta x goes to 0. And it's going, now, this part here is a 0. So we have a minus 0 up top. And then this part here, if we plug into our formula, for x, we have 0 plus delta x times 0 divided by x squared. So that's a 0 plus delta x squared plus 0 squared. And now let's get rid of this silly 0 here. And up top, we have a 0 times delta x. On the bottom, we have a delta x squared. That's a 0 there. And then at the very, very, okay. And then bottom, we have a delta x. But this doesn't really matter because we're taking a limit as delta x goes to 0. Delta x is not equal to 0. So 0 times something not equal to 0 is just plain old 0. And so we do have the partial derivative defined with respect to x defined to be 0. And by symmetry, same calculation with less bumbling, I hope, that's equal to 0 as well. So both partials exist at 0, 0. Okay, so that's kind of weird. Now, but I should also say the partial derivatives are not continuous. And here's why, not at 0, 0. Now, why is that the case? Well, once again, let's look at the x and then we can get the y by symmetry. So if we wanted to calculate this partial and we wanted to use a formula, so this is for x, y not equal to 0, 0, we just partially differentiate the expression xy over x squared plus y squared, where xy is not 0, 0. So then we're back to just plain old calculus 1 derivative. So use the quotient rule, which means you square the denominator. Then you take the derivative of the top. So the derivative of xy, and prime means take the partial derivative, times this, minus xy times this derivative with respect to x. And that's what you get. This derivative with respect to x is just going to be a y. So we have a y x squared plus y cubed. And then this derivative here, you just get a 2x out of it because that's a 0 and that derivative of x squared is 2x. So it's minus 2x squared y. And we get the following expression. You can combine these. So we get y cubed minus y x squared all over x squared plus y squared squared. And then factoring out a y, we get a y squared minus x squared. And then let's do one more factorization. So we get a y minus x, which is this factors into y plus x. Now, this function right here is not continuous. Xy being the origin. Now, why do you know that? And here's a proof. Let's look at a limit as, let's look at the limit as we approach the origin, but I'm going to let the x value be 0. So I'm going to approach the origin along x equals 0 along the y-axis. So if I let y go to 0 here, and I let my x equal 0, I have a y. Since I'm approaching along x equals 0, I have another y. And since I'm approaching along 0, I have another y. And on the bottom, since my x is 0, I have a y squared squared. So we'll have y cubed over y to the 4th. And that's a fairly easy calculation. And that does not exist. And depending whether you approach from y positive or y negative, you get plus or minus infinity. But this is unbounded. So the partial derivatives up here, the partial derivative exists at 0. So this is the upshot. So what we see is that we have the function that we talked about. In 0 if this function has partial derivatives but they're not continuous. So that is a little bit, that's a little bit of an advanced example to explain why partial derivatives are kind of weird. So I would just say thanks for watching, and there's a new keyboard I'm not used to. There's my escape. So thanks for watching.